Hi everyone, welcome to Sigma Maths. This is the first video in a series of videos looking at the sequences and series part of the A-level. In this video we will focus on the arithmetic sequences and series, and as you can see from the specification, you are required to know the formula for the nth term and the sum to n terms. We will also look at the proof for the formula to n terms and the first n natural numbers. Now we will do a few examples in this video, but if you're looking for a good amount of practice on arithmetic sequences, then check out the video after this one. Okay, so let's have a look at an example of an arithmetic sequence. Now, in case you didn't already know what an arithmetic sequence was, you may have called it in the past a linear sequence. This basically means that to go from one term to the next, you add or subtract the same amount every time. So looking at this example, we can see that to go from 2 to 9, we add 7. To go from 9 to 16, we add 7. And to go from 16 to 23, we also add 7. Now, when we are working with arithmetic sequences, this amount that we add every time is going to be called the common difference. It will be referred to in this way in the questions. And we also have the letter D to represent it. The very first term is also one of importance, and we will be calling that the first term, and it will be represented by the letter A. Now we also need to think about position in the sequence. We're going to use n to represent position, so n would be 1 for the first term, 2 for the second term, and then it will carry on in the same way. Bear in mind here that n will always be a natural number, which is an integer larger than 0. Okay, so if we try to have a think about writing out these arithmetic sequences more generally, to refer to each term in the sequence, we are going to be using u. So u1 would be our first term, u2 our second, u3 our third. So we're noticing here that the subscript on the u matches the position that we are in the sequence. So if we were to continue this on, we would eventually reach what we call un, which is known as the nth term. Now you will have been asked to find the nth term of linear or arithmetic sequences in the GCSE, so you may already know a way of doing this, but we do have a formula in the A-level that's based on the A and D values that we mentioned already. So let's have a think about what that formula is going to be. If we write out our general sequence, then we are going to start with A. We know that we're then adding D, our common difference, so our second term would be A plus D. The third term, we're adding yet another lot of D on, so that's A plus D, which would be A plus 2D. And we can carry on in this way. So what will we get to when we get to un? Now, occasionally students jump ahead of themselves a bit here and say, oh, that would be A plus ND. Unfortunately, that's not quite right. If we look at what the value of n is on each of these, n is 1, there is no d. N is 2, there's 1d. N is 3, there's 2d's. So actually what we've got here is 1 less than n, so n minus 1, d. So we have that un, our nth term, is a plus n minus 1 d. Okay, so we should pop that up in the corner so we can use that throughout the rest of the video. So this is our nth term formula that we have to know and use for arithmetic sequences. Now that we know that formula, let's have a go at doing a couple of questions before we move on to the sum. Okay, so in this question we have got the third and fifth term are given to us as 19 and 11. And we need to use this information to work out the first term and the common difference. Now, if you are very confident with arithmetic sequences, you can probably look at this and say, well, there's 2 lots of the common difference between the third and the fifth, work out the difference between 19 and 11 and work from there. But in the scenario where maybe the numbers aren't so nice or they're algebra, then I strongly recommend that we use our nth term formula to write down some equations, and then we can see what we can do with them. So remember what we said, so third term, n is 3, that would be represented as u3. Now this would be written down in terms of the nth term formula as a plus 2d, remembering it's n minus 1 lots of d, and we can see from the question that this is equal to 19. We do the same for the fifth term, so n equals 5, so we can write down u5 will be a plus 4d, and this must equal 11. So what we have set ourselves up here, and this does happen quite a lot in this particular section of the A-level, is a set of simultaneous equations. What's nice about these for the arithmetic sequences part is that we always have just an a term, which means we can just subtract to eliminate the a variable and solve the remaining equation in d. So a minus a, 0, 2d minus 4d, negative 2d, 19 minus 11, 8. And so here we arrive at negative 4 for our common difference. Don't forget that we've got to go back and work out the first term. So we could, for example, take equation 1, and from that, 1b, sorry, I should label them really, 1, 2. So from equation 1, we've got that a is 19, take away 2d. So that's going to look like 19 minus 2 lots of negative 4, which will be 19 plus 8, minus and minus. So we get 27. So we can see here that the sequence would be 27, and we're taking 4 every time, so then 23, then 19. Now I'm just writing, I don't have to write this out for the question, I'm writing it out just so I can check that using the information I have, which is that the first term is 27 and that the common difference is negative 4, that I do indeed get u3 is 19 and u5 is 11. So this is my check to make sure that what I've done is correct, and it seems to work out. Okay, let's have a look at the second question. Okay, we've got some algebra here. The first 3 terms of an arithmetic sequence are x squared, 6, and then x. Work out the possible values of x. So straight away we're noticing that s, meaning we can have more than one value. Okay, the way to approach a question like this is to think, if I know that it's an arithmetic sequence, that means I know that there is a common difference between every pair of consecutive terms. That therefore means that I can write down the difference as an expression for the first 2 terms. I can write down the difference as an expression for the second and third term, and these 2 things must be equal because they have to have a common difference. So my common difference for the first and second terms would be 6 minus x squared. So working out the difference between them. And then for the second 2 terms, that would be x minus 6. These 2 things must be equal. So there we have an equation that I can now solve. This is looking very promising because it is a quadratic equation, and we already know that we are looking for more than one value of x. Now, knowing it's a quadratic equation means we're going to want to write this in a way where we have our ax squared plus bx plus c form equals 0 on the other side, preferably with a positive x squared term. So in this case, I'm going to want to move my x squared term and my 6 over to the other side. So we have a 0 on the left-hand side. That means we're going to have an x squared. Plus x will still be there. And if we take the 6 away, negative 6, take away 6, negative 12. Okay, this looks like it was going to factorize, which is rather nice. So we're adding to make 1, multiplying to make negative 12. That will be plus 4 minus 3. So we therefore have that x is either negative 4 or 3. Okay, so let's just, we can stop there if we want, that's all the question asks for, but let's just check out the 2 sequences that we would get, make sure they make sense as arithmetic sequences so that we can feel assured that we have done the right thing for this question. So, option 1, x is negative 4, what will this look like? X squared would be 16, then we would have 6, and then we would have negative 4. To get from 16 to 6 we would take away 10. To get from 6 to negative 4 we would take away 10. It appears to have a common difference. We're okay with that one. Possibility 2, x is 3. Okay, well 3 squared is 9, then we would have 6, then we would have 3. To get from 9 to 6 we take away 3. To get from 6 to 3 we take away 3. Again, a common difference is appearing, so we can be sure that this is an arithmetic sequence. Okay, wonderful. Now we need to move on to the other section of this, which is series. Okay, so a sequence then is a list of numbers. That's when you see the commas in between them. They're the ones that we've been dealing with so far. A series, however, is when we take all of the terms in the sequence up to a certain point and we add them together. Okay, so a series is all about adding the terms in a sequence. And we have a formula for what we call sum to n terms, and you are required to reproduce the proof for this formula in the exam. So I figured we would start with the proof to show you where the formula comes from, and then we will have a go at utilising that formula. We're also going to have a look at proving the sum to n terms for the first n natural numbers, seeing as it is mentioned in the specification. Okay, so we need to lay this out quite nicely, the proof, because it requires a few things lining up for it to look really good. So I'm going to start all the way over to the left-hand side here, and I'm going to write out Sn. Now this is my sum to n terms. Sum to n terms. A bit like my un was the nth term. Sn is my sum to n terms. And let's see what this would look like generally. So the first term of our sequence we already know is represented as a. And our second term would be a plus d. And our third term would be a plus 3d. Notice that I'm putting plus signs in between the terms rather than commas because we are now dealing with series. This would continue, so I'm going to put a dot 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 to show that it carries on in the same pattern. And then I'm going to think about what happens on the other end. So I'm going to go all the way to the end of my series, and the very last term to add on would be the nth term because I'm summing to n terms. My nth term is my a plus n minus 1d, so I can pop this on the very end, a plus n minus 1d. Now the term before that is going to be minus d off of this term, so one less lots of d. So we still have an a, but this time it would be n minus 2 lots of d. And then the term before that again, a plus 1 less d, so n minus 3 lots of d. Now I wouldn't bother doing any more than the first 3 and the last 3 terms of the sum. You might get away with this the first 2 and the last 2, but I think 3 is about right. Now the trick to the proof and the trick to getting rid of this dot dot dot, which is kind of messing up my formula at the moment, is to write the sum to n terms out again, making sure that we write Sn again on the left hand side, and you'll see why in a minute. But we're going to write it out backwards this time. Now I already mentioned about lining things up, and what we want to do is we kind of want to line things up with these pluses that we've put in place of the commas. So my first term here, I've left quite a bit of space around it. That's because I know underneath I'm going to want to write the last term, a plus n minus 1d, which takes up quite a bit more space than just the a. Now I can get these pluses lined up. And then I've got a plus n minus 2d. So I'm literally just writing this out backwards. A plus n minus 3d plus dot dot dot. And then we have, oh, apologies, I have just noticed, you're probably thinking this quite a while ago, that I have put a 3 here. I probably said 3 as well, and I meant a 2. Otherwise that wouldn't be following the arithmetic sequence that we know goes up by d every time. So a plus d, a plus 2d. There's me just demonstrating how easy it is to make a mistake. Although it's quite common to make a mistake and then notice it again in your working, as you've just seen me do there. So I was looking, just before I wrote this term, I was looking at these two terms thinking, That's not right. I know that the 3 and the minus 3 don't cancel out. It made me suspicious. So I checked it. I spotted a mistake. So well done if you had spotted that already. Okay, so let's write this out. A plus 2d. Plus is roughly lined up. A plus d. And then finally a. Okay, we're going to see something nice happen here because we are going to add these two together. So now I'm going to attempt to draw a line all the way across. Okay, that's not going to be the neatest. It's not too bad. Okay, so put our equal sign back in. Sn plus Sn, 2Sn. Do not forget this little bit on the left hand side. What do we have here? Well, we've definitely got two A's if we add these together. And then we've just got n minus 1d. What about in this section here? We've got two A's again. And we've got a d plus n minus 2d. So we're adding on an extra d onto the expression n minus 2d. That must bring us up from n minus 2 to n minus 1. N minus 1d. And again, two lots of a. We've got n minus 3d here, and we're adding on an extra 2d, so that brings us up from minus 3, brings us up 2 this time, to n minus 1d. And we are noticing now that this is going to continue on exactly the same. I'm not going to write out more than those three terms, because I would be writing the same thing, and my ... should signify that I know this is carrying on in the same way. Exactly the same. Every time there's two a's, and there's n minus 1 lots of d. This is good news because it means that we can collect all of these terms together. Okay, so how many of these do I have? Well, it's sum to n terms, so I must have n of them. So that means I can put an n. Now I'm going to use square brackets here, and that's because I've used normal brackets for the n minus 1d. And when I use two sets of brackets in a formula or an equation, I quite like to use the square brackets so that I do not get confused. Okay, and then the last thing we need to do here is divide by the 2. That's why we needed to not forget what was going on down the left hand side here, because we needed this 2 to come in. So we've got n over 2 lots of 2a plus n minus 1d. And there we have our sum to n terms of an arithmetic sequence. Now when they ask you to prove things like sum to n terms of the natural numbers, which we are going to do in just a moment, then laying it out like this is a very solid way of doing the proof. Don't just rely on this formula. A real proof is to go from first principles, so writing out the sequence like this and then arriving at a formula afterwards. So let's have a go at the sum to n terms of the natural numbers. We're just going to pop our new formula up here. Okay. So we are doing the sum to n terms of the first n natural numbers. So natural numbers are, I mentioned this earlier, the positive integers larger than 0. So that means we are going to want to write it out very similar to the last time, so Sn, but this time we're just going to be writing 1, because it's a very particular sequence we're looking at, plus 2, plus 3, plus ... And the very last term we would add on is n. The term before that would be n minus 1, and the term before that would be n minus 2. Write this out backwards, so n minus 1, n minus 2, 3, 2, 1. Okay, we add. So exactly the same process as we use for the general series, 2Sn. And then we know, well, we should expect that when we add these, we are going to get the same thing appear over and over again. 2 plus n minus 1 is n plus 1. 3 plus n minus 2 is n plus 1. And we can see, I'm going to put these in brackets to make them stand out even more. It's going to be the same thing over and over again. Again, how many are there? Well, we're summing to n terms, so there are n of them, so nn plus 1 And then finally, we divide by 2. N over 2 times n plus 1 can be written as a half n plus 1. Could also be written as n plus 1 all over 2. All of these are equivalent. Okay, so if you write it in a different way, does not matter, is all the same. So we can use this method of writing out the sum, writing out backwards, adding them together, collecting like terms, and then halving to prove the sum of any arithmetic series. Okay, prove the sum of any arithmetic sequence, which therefore is a series. Okay, we're going to have a go at a couple of questions just to demonstrate what we've just learned, and then that will be the end. Okay, so question 3. Find the least number of terms of the series -2 plus 4 plus 10 plus 16 to exceed 500. Now, whenever you start a new question on sequences and series, I strongly suggest that you write down the parameters involved. So here, bear in mind our sequence would just be these numbers but with commas in between. We've got a is -2, that's our first term, and d, what appears that we're adding 6 each time, so d would be 6. Now, because we have pluses in between them, we know it is Sn. So one of the mistakes I see is misunderstanding the question and using the wrong one of these two formula. Okay, so if this was just find the smallest term in the series to exceed 500, then we would use un because we'd be looking for a particular term. But this one is a series, so we know we are using Sn. So let's write down the formula with the numbers that we have. So Sn equals n over 2. 2a here would be -4 plus 6 lots of n minus 1. So let's just put in d is 6 to the formula. Let's tidy this up a little bit. N over 2. So that's going to be 6n minus 6. So I can bring this forward, 6n and minus 10. And just a tiny bit more tidying up. We can divide through by 2, so n and then 3n minus 5. Now, we are exceeding 500, so this is where we turn this into an inequality. There we go. Multiply out the brackets. 3n squared minus 5n. Subtract the 500 because we've spotted it's a quadratic, so we know we need to get everything onto one side. Now, we need to solve this quadratic to find the root that we're working with, and then it is a quadratic inequality, so we need to be very careful about not just sticking this greater than sign in place of the equal sign as if we were solving. Okay, so unfortunately we cannot factorize this quadratic, but if we put it into our calculators, then we discover that we have if this was equals to 0, we have two possible roots, 13.8, that's rounded there, or -12.1. Now, I always strongly recommend that when you are solving quadratic inequalities, you do just a quick sketch of the quadratic so you can be sure that you are choosing the correct range of values. So we have -12-ish or 13, and it's a happy quadratic, a positive n squared. So our curve is going to look something like that. It's not the best quadratic, I'll admit, but it's got roughly the right shape. We want greater than 0, so we're above the x-axis, so we want these bits here. Therefore we want larger than 13.8 and smaller than -12. So let's just write those down and then we will think about the context of the question. So we either want smaller than that or larger than 13.8. I have rounded these to one decimal place. I already know that I'm not going to worry too much about the decimals because my answer does have to be an integer because n is the position in the sequence. So I'm going to be, picking the next integer up anyway. Just a note there. So this one, we just put a little cross under that to show that we know that it's not helpful to us because we're looking for a positive value of n. And then here we're looking for the first integer above 13.8, so we can conclude then that n is 14. Okay, so it takes 14, at least 14 of the terms in this series to reach a total of 500 or more. We are done. Okay, last question of the video. Prove that the sum of the first 2n odd numbers is 4n squared. Now, it is a proof, which means we should really be writing it out like we did for Sn and for the natural numbers example that we did earlier. So the first 2n odd numbers. Okay, so let's start writing out the sum to 2n terms of the odd numbers. So we start with 1, leaving ourselves a little bit of space just in case the last few terms are quite large. So 1 plus 3 plus 5 plus ... Now we need to know what we're ending on. And just so we don't make any silly mistakes, I would suggest that we actually work out the nth term for the odd numbers, and then we can just pop 2n in there, because we've noticed it's not just the first n odd numbers, it's the first 2n, and we can be certain that we have actually got the last odd number in the sequence where n is 2n. So a is 1 here, d is 2, the un therefore is 1 plus 2 lots of n minus 1, which would be 2n minus 1. Okay, so if we look for u2n then, so that we know what the 2nth number in this sequence is, then we would do 2 lots of 2n minus 1. So I'm just substituting in 2n in place of n in the formula, and we would get 4n minus 1. So we go back into go right to the end. So the very last term is going to be 4n minus 1. The one before that is going to be, now be careful here, it's going to be 4n minus 3, and that's because we are going down in 2s, unlike the natural numbers where we just took 1 off each time. And then we are going to have 4n take away 5. There we go. And we can write this out again, but backwards. So 4n take away 1 plus 4n take away 3 plus 4n take away 5. There we go, ... 5, 3, and 1. I'm going to add these together. There we are. So 2sn, 1 plus 4n minus 1 is 4n. 3 plus 4n minus 3 is 4n. We can see this is going to work out quite nicely. 4n every time. Now remember, this time there are 2n's. Lots of little ways you can get caught out in this question. There are 2n lots of these terms. So it is 2n lots of 4n. And then finally we can divide by 2. N lots of 4n, which we can simplify to 4n squared. And we have arrived at the answer in the question. Okay, so that brings us to the end of this video. As I mentioned at the beginning, if you're looking for more practice on arithmetic sequences and series in particular, then the next video will contain a range of questions on them. The videos after that are going to be looking at the geometric sequences and series. They're the ones that you multiply every time. And then following that, we will be having a look at sigma notation. Okay, well, if you enjoyed the video and you found it helpful, then please don't forget to hit the thumbs up button. Thank you very much for watching, and I look forward to seeing you in the next one. Bye.